Okay, so welcome, and we'll pick up where we left off here in chapter 11. And again, like usual, if you do have questions, feel free to ask them in the chat box. So where we left off was we were talking about sort of organic chemistry. Again, we got into sort of a little overview of organic chemistry. Again, usually organic chemistry, for the most part, is made up of compounds that contain carbon, and the basis of a lot of organic molecules are kind of like what we see on the screen here is carbons attached to carbons, and those carbons attached to hydrogens, and that's your basic sort of connection that we see. As we also talked about, there's a lot of different sort of categories of organic compounds, and they're sort of classified by certain aspects that you find on the molecule, and those sort of aspects that we find on the molecule are sometimes referred to as functional groups. And depending on the functional group that's there, will give you a different type of organic molecule. And they will also have obviously some different properties depending on the functional group that's present. We talked about a little bit of sort of the basic functional group, which is sort of the carbon-carbon single bond. And those are a group of organic molecules which are known as alkanes. So that's sort of where we're at. Alkanes functional group is the carbon-carbon single bond, which means pretty much they have all single bonds in there, no double bonds or anything like that. And that is what is sometimes referred to as a saturated hydrocarbon. Saturated means that it has the maximum number of hydrogens per carbon. And when we talk about carbon, remember carbon pretty much wants 4 bonds. So it's going to continue to make bonds until it has 4. And pretty much hydrogens will kind of fill those in. And that's not to be confused with alkenes, for example, that have a functional group of carbon-carbon double bond. And those are what are referred to as unsaturated hydrocarbons. And those are unsaturated because, as we also talked about last time, every time you put a bond on, you do have to sort of sacrifice 2 hydrogens to make room for it. Otherwise, you'll have too many bonds of carbon. So we started talking about, I think we did get kind of the first 10 alkane names, and we're kind of in the middle of that right now. And the first 10 alkane names are really important because everything in organic chemistry is pretty much based off of those first 10 names. So that's like methane, ethane, propane, butane, pentane, and so forth. And everything really does come back to those. So continuing on here, butane, for example, is 4 carbons in a row, as we see there on the bottom. And this is a straight chain here of butane. And that's 4 carbons in a row, which is butane. On the bottom is what is sometimes referred to as isobutane, or really the IUPAC way of naming it is 2-methyl propane. And as we also talked about last time, I think at the very end, sort of a way you could distinguish certain compounds is by naming them, and we're going to get more into how to name those here today. But one of the sort of key things that you do when you go about naming things is trying to find the longest continuous carbon chain. Again, that carbon chain doesn't have to necessarily be the straightest, but it does have to be the longest continuous carbon chain without you kind of going backwards or backtracking or anything like that. So essentially you start one way and sort of go until you hit a dead end. And again, the longest chain of carbons gives you really the base of the name. So here, this was pretty easy to see. You got 4 carbons straight across. And again, 4 carbons is really butane. As opposed to when we come down here, we really have 1, 2, 3 carbons. Again, is the longest continuous carbon chain. You also could go 1, 2, and upwards if you want 3 carbons as well. But the longest continuous carbon chain without backtracking is only 3 carbons. And 3 carbons is based off of propane, which is where that part of the name comes from. And this is what is sometimes referred to as a branch chain, as we talked about as well. Off of that longest continuous carbon chain, there's other things attached. And these are sometimes referred to as groups. And these are sometimes referred to as alkyl groups. And a group really is something that's attached to the longest continuous carbon chain. That's, again, not part of the longest continuous carbon chain, but attached to it. And that is where the 2-methyl comes from because of the location of this group. It's on carbon number 2. And that's where the 2 part of the name comes from. And the methyl part comes from the name of this group, as we will also talk about here in just a second. It has 1 carbon, which is based off of methane. But since it's not part of the longest continuous carbon chain, it's a group. We put a YL at the end of it, and that's where the 2-methyl part of the name comes from. So again, an important thing, especially when you go about and start naming things, is you do want to always try to find that longest continuous carbon chain. We also touched upon this idea as well, and the idea of isomers. And isomers, again, are really something that has the same molecular formula, but has a lot of times, for example, a different sort of connectivity, if you will. And also, because it does have a different connectivity, it would have a different name. And for example, here, the 2 that we just saw there on the previous page, the butane and the isobutane, are the 2-methylpropane. They are isomers of each other. So again, the one that we were just looking at here, if we count up pretty much all the carbons and all the hydrogens on both of those guys, again, we have 4 carbons and 10 hydrogens. And same thing down here, we have 4 carbons and 10 hydrogens. So they both have the same molecular formula, but they do definitely have a different connectivity. And as we can see here as well, a different name. And thus they are what are known as isomers of each other. And because they have different names, they will also have obviously that different connectivity and will have different properties as well. And again, that's basically what an isomer is, same molecular formula, different sort of connectivity. There's several different types of isomers. One type of isomer is a constitutional isomer, and constitutional isomers differ in the way that the atoms are connected to each other. So same thing down here, if we sort of count up everything that we got going on, we got 2 carbons, 6 hydrogens, and 1 oxygen. Same thing on the right-hand side, we have 2 carbons, 6 hydrogens, and 1 oxygen. And the way that they're connected is completely different, and they would have different names. This is ethanol. This is what is known on the right as dimethyl ether. These are actually 2 different types of organic compounds. We talked about functional groups last time. So this OH group here is the functional group for an alcohol. Again, this would be the functional group. While this little run here of carbon, oxygen, carbon is an ether. Also a very different sort of organic compound as well. Again, although they do have the exact same molecular formula, because of the way they're connected, they are known as isomers of each other. They're also very different in terms of their properties. So for example, the ethanol on the left can do some hydrogen bonding because it has that oxygen hydrogen. For example, the guy on the right cannot. And because the guy on the left can do some hydrogen bonding, it's expected that it would have something, for example, like a higher boiling point, right? So the stronger sort of that intermolecular force, like hydrogen bonding, the higher the boiling point. So something like on the left there would be a higher boiling point. In terms of sort of a reactivity as well, I don't know if reactivity is the right word there, but in terms of solubility, for example, in water, the guy on the left also would be much more soluble than the guy on the right. Again, because the guy on the left has the ability to hydrogen bond with water, while the guy on the right does not necessarily have that ability. So, you know, a lot of these things, even though they are technically the same thing in terms of elements and so forth, they are very sort of different a lot of times in terms of properties because of those connectivities that we see. Here's pentane, and pentane again is 5 carbons. And if you remember what we talked about last time with alkanes alkanes have that general form of CnH2n plus 2. Again, here, if carbon is 5, 5 times 2 is 10, plus 2 is 12 hydrogens. That's a 10. Let's make that a 12. There we go. That's 12 hydrogens, and that's what we see here. So this would be pentane. Again, just a straight old chain of carbons attached to carbons. That's sort of the condensed formula. Again, the more structural formula would be something like this, where we draw it out. And again, obviously the hydrogens all the way across. Here's also 2-methylbutane and 2,2-dimethylpropane. These are all, if you count up everything here, 1, 2, 3, 4, 5 carbons, 3, 5, 8, 11, and 12 hydrogens. So again, they all have the exact same formula, but they are different. So if we look here, we have 1, 2, 3, 4 carbons is the longest run of carbons you could get. And that is where the base of the name comes from, which is butane. Again, here we have this guy right here, which is a group. And again, it's a 1-carbon group, which is known as a methyl group, which is where the methyl part of it comes from. And the number 2 means that if you count the carbons, 1, 2, 3, and 4, this is at carbon number 2 is where that name comes from. So that is 2-methylbutane. Same thing here, though it has the same formula, the C5H12, longest continuous carbon chain is only 3 if you go straight across. If you go straight across and up, it's 3, right? 1, 2, and 3. If you go straight across and down, it's also 3. And again, 3 carbons is propane, which is where that is from, that name. We also have this guy and this guy, which are both methyl groups. And there's 2 of them, which is our dimethyl part of the name. And again, they are both here at carbon number 2, which is where the name comes from, the 2,2-dimethylpropane. So again, these are all isomers of each other. They all have the same molecular formula, but different connectivity. Again, going to have some different properties as well. Straight chain here, pentane, and more branch chains over here at both of these ends. So here's the rest of the first 10 alkanes that we also touched upon last time as well. And again, really important to know those first 10 because everything pretty much based off of them. So let's actually talk about how we sort of name these guys. And we've sort of touched a little bit on it as we've been talking. But really, usually when you go to name, we usually name for the IUPAC way of naming. Again, the IUPAC way is the International Union of Pure and Applied Chemistry. Again, they are the guys that basically come up with all the naming that we do, pretty much with everything. And that's usually the way that you sort of go about naming organic compounds. As we also touched upon last time, there are lots of different names for the same compound in organic chemistry. Again, some are historical type names, some are common names, and then obviously some are like the IUPAC name. So it is very, very possible that you could come across an organic molecule and you'll actually have, for example, 3 different names for the exact same thing. But for the most part, in most classes that you take, if you should continue on somewhere where you're doing some organic chemistry, the IUPAC name is sort of like now the more official name, if you will, and usually the name that you use and sort of go. So really, there's a couple different sort of steps when you go about naming an alkane, for example. And really, naming an alkane or anything else, the first really big thing that you need to figure out is the longest carbon chain that we've been talking about a little bit. And again, when you do count the longest continuous carbon chain, it doesn't necessarily always has to be the straightest. So for example, see if I can, a little bit of room here. So let's just say we have, you know, this sort of guy here. I'll put in some hydrogens here, maybe. And we do this guy here, pop some hydrogens in. Should do less carbons. Let's see. There we go. So obviously on this first one, if we just count straight, we have 1, 2, 3, 4, 5, 6, 7 carbons is the longest continuous carbon chain, and 7 carbons would have a base name of heptane. So that longest continuous carbon chain would give you your base of your name. But now if we come over here to the guy on the right and we start sort of looking for the longest continuous carbon chain, again, if we just go straight here, we have 1, 2, 3, and 4. And you may say to yourself, well, that's 4. So that looks like the longest continuous carbon chain. But again, here, you got to sort of look at all of your options. So you could technically go this way, 1, 2, 3, and then go up 4, 5, and 6. And that would give me 6 carbons going obviously the orange way. You also should always check every sort of option that you could have. And really your other option in terms of sort of ways would be, for example, if you went, say, this way, 1, 2, 3, 4, and 5. So we got 5 carbons that way. And then we obviously had 4 carbons going the purple way. So we could see, looking at all of our options, the longest continuous carbon chain, this guy had 4 carbons going in purple, is going in the yellow path. And sometimes once you find that longest continuous carbon chain, which in this case would be 6, again, that's going to be hexane as the base of the name. I find that if you want to name it, it's sometimes really good to kind of put a little box around it, if you will. And once you put the box around it, you can see what is part of sort of the main chain. And what you end up with is, as you can see there is something that is not really part of that main chain. And again, anything that you find that's on that structure that is no longer part of the longest continuous carbon chain, again, is what is referred to as a group. And if it is a carbon containing group, it's an alkyl group. And really naming in terms of organic chemistry is all about sort of location. And you're basically telling everybody exactly where you can find things and what is there and where it is. And that's really the basis of sort of this naming. So again, hexane would be the base of our name. Now, when we look at what's attached there in terms of that alkyl group, it is based off of 1 carbon. And even the groups that are attached that are not part of the main chain are also based off of those first 10 alkanes. So since it has 1 carbon, it is based off of methane. Methane, though, is CH4, as we will see. I think I might be jumping a slide here, but we'll just talk about it here as well. But methane is CH4. The problem with methane, though, is if I wanted to put it onto this longest continuous carbon chain, in order for it to attach as methane, you would need to put another bond, right? Just like that. And the problem with that is now you would have 1, 2, 3, 4, and 5 bonds. And if you remember, 4 bonds, it's all carbon can have, right? So that's too many bonds. So when it is a group in 1 carbon, what we have to do actually is get rid of one of those hydrogens. And when we get rid of one of those hydrogens, we get a CH3 group. And the CH3 group is good because this spot right here, which in methane is a hydrogen, now is open to bond to, say, a carbon. And this CH3 part of it which is an alkyl group. An alkyl ends in YL, goes from methane to a methyl group. So we drop the last part of methane and we put YL, again, to indicate that it's a group. It has one less hydrogen than methane, and that one less hydrogen gives it a place to be able to connect without having too many bonds. Any questions on that? I see I was one slide for that, but yeah, so that's essentially what we're talking about here. So once we find that longest continuous carbon chain, again, anything that is not part of that longest continuous carbon chain will most likely be one of these alkyl groups, which again is just a word that basically means it's a carbon containing group. And it is a carbon containing group that basically lacks one hydrogen. And the lack of that hydrogen, again, gives it the ability to bind into the longest continuous carbon chain without having too many bonds. And as you can see, just like we did with the methane, we drop the ANE and we put the YL. If we had, say, a 2-carbon group, again, a 2-carbon group would be based off of ethane, which is this guy. But again, the way ethane is exactly like that. It has no way to bond into a chain because it has too many. So we essentially will drop one of the hydrogens off, and what we'll end up with is something like this. And again, missing that hydrogen there gives it a place to attach without having too many bonds. And it goes from ethane to a ethyl group, YL at the end of it. And that's what we see here. So pretty simple, again, based off of those first 10 alkanes, you drop the ANE, you put the YL. It also, again, will have one less hydrogen, again, to allow it to connect in. Here are some alkyl groups. You have a similar table in your book, I think. Methyl, ethyl, this is propyl, again, 3 carbons based off of propane. Butyl, 4 carbons based off of butane, a pentyl, a hexyl, and so forth. Each of these based off of those first 10 alkanes, one less hydrogen to allow it to bond. Now, there are some groups that are have special names and sort of special arrangements. And this is isobutyl, sec-butyl, T-butyl, but this is probably the common one here. This is what is known as isopropyl group. And isopropyl group looks something like this. And again, the connection happens here. And this is what is referred to again as the isopropyl group. You may say to yourself, how is that different than, say, a propyl group, which looks like this? And really the difference comes from sort of where it connects. Now, when we talk about carbons, there is a way to classify carbons. And for example, if you have a carbon that's attached to one other carbon, so this guy right here would be known as a primary carbon, or the one with the little circle on top. And that's basically this carbon right here that's circled is attached directly to one other carbon. You could also have a carbon, for example, that is attached to 2 other carbons. And that is what is known as a secondary carbon. And you also could have a carbon that is attached to 3 other carbons. So again, if we look at this carbon here, it's 1 carbon there, 2 carbons there, and 3 carbons there. And this is what is known as a tertiary carbon. And the difference in sort of where the attachment occurs, it gives us sometimes some different groups. And again, the guy on the right here is a propyl group, or a normal propyl group. And the attachment that occurs for this group to, say, the longest continuous carbon chain, it happens at the primary carbon. Again, this is a carbon that's directly attached to one other carbon. While over here in the isopropyl group, the carbon that's attaching to the chain is this guy, which is attached directly to one and two other carbons. And this would be a secondary carbon. So these sort of attachment places and how they attach, depending on sort of which carbon it attaches to, will give us some different groups that occurs. And that's why when we look over here, for example, this is what's known as T-butyl or tert-butyl. T-butyl or tert means tertiary, basically. And if we look at the carbon that gets attached, it's attached to 1, 2, and 3 other carbons. And that would be a tertiary carbon. This guy right here is attached to 1 and 2 carbons. And again, that is why this is considered a secondary carbon as well. So honestly, you don't have to worry about probably too many on this slide. This guy again, though, the isopropyl does come up a lot. And it is sort of a historical type of name that isopropyl group and used and really kind of named that way a lot as well. All right, so let's go through sort of naming these guys here together and sort of talk about what we want to do. So if we take this one here that we have on the screen, again, the first thing that you want to do is locate the longest carbon chain. So we got 1, 2, 3, 4, 5, and 6. We also, by the way, could get 6 if we went 1, 2, 3, 4, 5, and 6. And the last option would go 1, 2, and 3, which is obviously less than 6. So again, you can get sort of sometimes the same number in terms of longest continuous carbon chain, no matter which way you sort of go. I always recommend, though, if you have multiple ways to get to the same number, I would probably choose the straightest. Sometimes it's easier to see. And that's sort of what they did here. So they put a box around the longest carbon chain, and that's usually a pretty good thing to do. And again, 6 carbons is based off of hexane. So that becomes sort of your base of the name here. Now, when we look at this, we also want to find anything that is attached to that longest carbon chain, but not part of the group, our longest carbon chain. And again, this is going to be our group. This group, again, has 1 carbon, which is based off of methane, but because it's a group, it is a methyl group. So we have a methyl group attached to this hexane. But like I mentioned before, the whole goal of naming really is about location. So we need to give the location of where we find that methyl group. And to give the location, really, you need to number the longest carbon chain. So if we number the longest carbon chain, this is 1, this is 2, this is 3, this is 4, this is 5, and this is 6. Now that is one way that you can number that longest carbon chain, in this case going left to right. We also could number the other way, going 1, 2, 3, 4, 5, and 6. So those are really 2 different ways that you can number the carbons, and going left or going right. And what you want to do basically is give the location of that methyl group. So if I went the green way, my methyl group would be at 5, and it would be a methyl group, carbon number 5. If I went the purple way, and I wanted to give the location of that methyl group, it would be at carbon number 2. So one of the important rules when you're naming alkanes is once you have the longest continuous carbon chain, you want to number it whichever way gives the group the smaller number. So it's always smaller number. Yeah. So that is sort of the goal here. So you want to go with the smaller number. And in this case, the smaller number for that group is 2. So we would use that, and this become 2-methyl hexane, all kind of one word. The 2-methyl means that at carbon number 2, we find our methyl group. Hexane means we have a chain of 6 carbons in a row. And the name of this guy again would be 2-methyl hexane. A couple of little things when we do name, you see a dash that I put here, and between a number and a letter, we put a dash. Now, if you should have 2 numbers that come back to back, we put a comma between those when we name them. And the last thing is, when we're naming these things, all the groups go in alphabetical order. So the groups go in alphabetical order, regardless of number. And we do kind of use those little things. So again, if you have a number to a letter, we put a dash between it, which is, again, why this dash is right here. Number here to letter here, we put a dash between it. And again, 2 numbers, we do a comma. Any questions on that? And again, this is a good sort of reminder as well that even though it may be drawn slightly different when you're counting those longest carbon chain, you do want to follow it in every sort of conceivable pattern. So here, obviously, 1, 2, 3, 4, 5, 6. Again, here, 1, 2, 3. And you shouldn't stop, even though, you know, there's nothing to the right, but it does continue down this way, 4, 5, and 6. And even this guy, the way it's drawn, 1, 2, you should go down, 3, 4, 5. You can even go back up or down if you like. And you can see in each case, the longest continuous carbon chain is our 6. And in each case, the name of all these guys would end up being the same. It would be the exact same thing as we just did there. Each of these guys here would be 2-methyl hexane. Again, just to show you, this is the one we just did. With this longest carbon chain, there's our guy at carbon 1 and 2. And over here, for example, this would be our methyl group. And in this case, we would number this way, 1 and 2. So these all would be 2-methyl hexane, even though they look very different in terms of the way they're drawing. And that's why, again, you always want to sort of go with all your options in terms of longest continuous carbon chain to figure out which one it is. All right, so we did that. We got to naming those groups by numbering. Get the idea there. Another sort of thing that does happen, like we saw on a previous sort of slide, is sometimes you will have more than one of the same group in a molecule. And we do use a prefix to indicate that. So let me back it up here and find that one that we just saw earlier. I think it was right before here, I think. That's right here. So for example, again, if we sort of approach this from our knowledge right now, again, let me just maybe redraw it to make it a little bit neater here. So if we do this again, no matter which way we go, if we go straight left to right, we have 3 carbons. If you went left and then went up, you also have 3. If you went right and you went up, you have 3. If you went right and you went down, you have 3. If you went left and you went down, you have 3. So no matter which way you go in this guy, you will have 3 carbons. Again, the straightest is probably the easiest. 3 carbons, again, going to be our propane in terms of our name. Now, when we look at this, kind of like what we talked about a little bit earlier, attached to this here is a methyl group here. Attached to here is also a methyl group. So we have 2 methyl groups in that compound. So 2 methyl groups, the prefix for 2 is di. So we have dimethyl would be our groups there because there's 2 of the same. It doesn't necessarily mean that they has to be on the same carbon. It just happens to be in this case. And if we number this left to right is 1, 2, and 3. Or if we go right to left, it's 1, 2, and 3. In this particular case, and it does happen, it really doesn't matter which way you go. If you went left to right, those groups would be at carbon number 2. If you went right to left, they would be at carbon number 2. 2 is the smallest number. What is important in this case is you do have to give the number for each of the methyl groups, even if they are the same number. So that's why we have 2, 2 dash dimethyl propane. The first 2 is for the first methyl group at carbon number 2. The second 2 is for the second methyl group, also found at carbon number 2. The dimethyl means that in that molecule, there's 2 methyl groups. Again, they don't necessarily have to be at the same carbon for to be dimethyl. But we do see what we talked about as well. Between 2 numbers here, we have a comma. Between a number and a letter here, again, we have a dash. So again, you will see some multiple groups in a compound, and we do use those prefixes to help us sort of name those. And again, here, I guess I could just went forward, would have been good as well. Here as well, if we look at it, we have a methyl group here and a methyl group here. In this case, not on the same carbon, but we would use dimethyl for it. So if we were to name this guy, again, longest carbon chain, they boxed it for us, which was nice. So we got 1, 2, 3, 4, 5, and 6 carbons. So again, the base of this name, because it's 6 carbons, would be hexane. We obviously have the 2 methyl groups, so we would have dimethyl. And again, we need to give the location, so we want to number this chain. And you do have 2 ways to number it. So let's take a look here. If we go left to right, this is carbon 1, this is carbon 2, this is carbon 3, carbon 4, carbon 5, and carbon 6. That means that group number 2 and 3, we have a group. If we went right to left in terms of the numbering, this would be carbon 1, this would be carbon 2, this would be carbon 3, this would be carbon 4, this would be carbon 5, and carbon 6. And if we went right to left, we would have a groups at 4 and 5. So again, when we're choosing numbering, we want to give the groups the smaller number. So in this case, we would not use the green way of numbering. We would want to use the orange way of numbering, which gives those groups the smaller numbers. And putting that together, again, we need to give the location of each of those methyl groups. So that would be 2, 3, again, a comma between the 2 numbers, dash between number and letter, dimethyl hexane. So this would be 2, 3, dimethyl hexane. Again, it's really all just about location. It tells us basically if we go to carbon number 2 and we go to carbon number 3, we should find a methyl group on a long chain of 6 carbons, which is the hexane. Any questions on that? All right. So we're kind of going through. I'll just put it up here so you can see it. But sort of what we talked about. Again, we do want to put everybody together in terms of alphabetical order, in terms of the groups. So again, if the groups were different names, like a methyl and an ethyl, the ethyl would come first, ignoring prefixes and also ignoring numbers, you know, in terms of lower number first or something like that. So alphabetical sort of takes the lead there, and that's going to give us our 2-methyl hexane, which we saw earlier. And hopefully we get the same thing if we just got here. Again, I'll just put it up here so you can see it in case you want to look at that later. 2, 3 dimethyl hexane. Again, the location of everybody. All right, so let's take a look here. Why don't you take a second and why don't you give this guy a name and see what you come up with. And we would also have an ethyl group. We do want to number it in a couple of different ways. We could go left to right, which gives us our group numbers as we see here, 2, 5, and 6. We could go right to left, which would give us 1, 2, 3, 4, and 7 if we go the other way. So putting all that together in sort of alphabetical order, 5-ethyl, 2,6-dimethyl octane. Again, to go through it, 8 is our longest continuous carbon chain. So that's where the octane part comes from it. We have 2 methyl groups. Again, does not have to be on the same carbon, but we do have the dimethyl, and they are at carbons number 2 and 6. And then 5-ethyl. Again, even though number-wise, this guy is higher, E before M is what we're looking at in terms of alphabetical. So 5-ethyl, 2,6-dimethyl. Again, we see a dash between a number and a letter, also here as well. We also see a comma between two numbers in this case. Again, if we numbered the other way, 1, 2, 3, 4, 5, 6, and 7. So if we went sort of the opposite way, we would have groups at 3, 4, and 7, which again is a larger set of numbers than 2, 5, and 6. And it's really, when you look at these two numbers here, the 2 is less than the 5. The 2 is less than the 3. So that's why, again, we went the other way. All right. So why don't you try these couple here, see what you come up with in terms of the names, and then we'll talk about it. And by the way, there's 2 different ones there on the bottom. Okay, let us start going through and seeing how we're doing. Let's start with the top one. And again, we want to figure out the longest continuous carbon chain. So if we just do the straight way, we got 1, 2, 3, 4, 5, and 6. Now, if we go straight 1, 2, 3, 4, 5, and go upwards, 6. So that looks like 6 so far. If we go straight 1, 2, 3, 4, 5, so that's less. And our last, I think, couple of options here would go this way: 1, 2, 3, 4, 5, and 6. So, and the last way you could actually look is 1, 2, as I use all orange, 3, 4, 5, and 6 going that way. So again, no matter which way you sort of go there, it looks like we're topping out at 6. And let's just so let's go with just straight 6. Looks good. We'll just go straight across, I think, right? So we have 6 carbons, and again, the base of 6 is hexane. Now, when we look at those 6 sort of longest carbon chain, we also see a couple groups that are attached. So up here we have a 2 carbon group, 2 carbon base off of ethane, but because it's a group, it's a ethyl group. We also have a 1 carbon group right there based off of methane. With the loss of the hydrogen, it's a methyl group. So we do need to figure out numbering. So if I go left to right, I got 1, 2, 3, 4, 5, and 6. So left to right, I have groups at 3 and 5. If I number the opposite way here, going 1, 2, 3, 4, 5, and 6, I have groups at 2 and 4. So again, we want to go with the lower numbering, which is the 2 and the 4. So that means at carbon number 2, there is a methyl group. So carbon number 2, there's a methyl group, and a carbon number 4, there's an ethyl group. Now we do want to put this together in alphabetical order, which means even though number-wise, the E will come before the M here. So putting all that together, going to give us 4 ethyl, 2 methyl, and then hexane. Any questions on that name there? All right, so let's take a look at the guy on the left. Looks like we have 1, 2, 3, 4, 5, 6, and 7 carbons. Other option would be right to left, 1, 2, 3, and up was 4. We can then go 1, 2, 3, 4, 5, and 6 if we went up. So it does look like 1, 2, 3, 4, 5, 6, 7 is going to be our longest continuous carbon chain. Again, goes down and then goes up. Again, the basis of 7 carbons is heptane. And here we see we have just 1 group attached, and that would be our methyl group. So what is left is to figure out which way gives our methyl group the smaller number. If we go this way, that's 1, 2, 3, 4, and carbon number 5. And if we go right to left, 1, 2, 3, 4, 5, 6, and 7. So obviously going right to left gives our methyl group a number of 3. Left to right there gives us a 5. So we do want to go with the 3. So putting that together, 3-methyl heptane, all one word there. In that case, any questions on that naming there? Now, if we look to our guide to the right, there's a lot going on there. So let's see here. If we just go straight across, that is 1, 2, 3, 4, 5, 6, 7 carbons. All right. If we go straight across and then detour up, like so, that is 1, 2, 3, 4, 5, 6, 7 carbons. So you may say to yourself, that looks good, that's more. But again, you always want to sort of try all your options. So if we perhaps start up here, come down, come across, and then go up. If we count how many carbons are in there, that is 1, 2, 3, 4, 5, 6, 7, and 8 carbons. So again, you want to try all your options. As you can see here, not the straightest by any means. It does go down, goes back up, and all that good stuff. But 8 carbons is our longest carbon chain, which means we are going to have a base of the name that is based off of octane. We do have, in this case now, a couple of different groups attached. We have a 2 carbon group right there, which is a ethyl group. We have, I kind of wrote over it there, I'll circle it. We have a 1 carbon group, which is a methyl group. So we do want to do some numbering. And in this case, we want to make sure, again, numbering wise, we end up with the smaller numbers. So if I start numbering up here, this would be carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6, carbon 7, and carbon 8, which means if I go kind of the purple way, I have a group at carbon 2 and carbon number 5. The other option would be to number really the opposite way. And if we number the opposite way here, this over here in orange would be 1, 2, 3, 4, 5, 6, 7, and 8. And again, that means that I would have groups at carbon 4 and 6. So again, always the smallest numbering. So we do want to go the purple way here. And that's going to give us a name of, well, that's going to put, that's actually carbon 3. I'm sorry. There we go. It's actually carbon 3. Still works out the same though. So that's good. 3 or 5. So 3 is still lower than 4, which is good. So that would be 3 methyl here. And this would be 5 ethyl. Again, alphabetical. The E is going to come before the M. So this is going to be 5 ethyl dash 3 methyl octane. Any questions on how to name those? So again, you do want to make sure that when you're doing your options there, you do try to check all the different combinations. Again, when you're doing the longest continuous carbon chain, the really key thing is not to go backwards. So you can't back up and go a different direction. You pretty much got to start in one direction and go until you, again, hit sort of a dead end. And you do want to check all your options, as we saw there in the last one. Depending on sort of which option you choose, obviously you'll get the different number, but you always want to stop with the longest carbon chain. Any questions on those names there? Let's look at the top one here. So this top one here, we want to figure out the longest carbon chain. We have 1, 2, 3, 4, 5, 6, 7. If we go straight across, we have 1, 2, 3, 4, 5, 6, 7. If you go kind of down and across, we have 1, 2, 3, 4, 5, 6, 7. If you go that way. And I think that's all your options, kind of 1, 2, 3, 4, 5, 6. So it does look like 7 is pretty much the longest no matter which way you go. So if you do have that option, again, it's sometimes easier to see everything if you just take the straightest, especially if you do have that option. So if we just go straight across here, again, 1, 2, 3, 4, 5, 6, 7. So the base of our name is going to be heptane. Again, here we have a methyl group over here. We also have a methyl group over here. And we have a 2-carbon group over here, which is a ethyl group. So in terms of numbering and names, we do have dimethyl as part of the name because we have 2 methyl groups in the compound. We also have an ethyl group. So we do want to do some numbering. So let's take a look at the numbering options here. Going left to right, that's 1, that is 2, that is 3, that is 4, that is 5, that is 6, that is 7. That means going that way, we have a group at 2. I'm going to count right, hopefully this time, 3 and 5. We go the opposite way, going right to left. We have 1, 2, 3, 4, 5, 6, and 7. So going right to left, we have a group at looks like 3, 5, and 6. So again, 3 being bigger than 2, going to be too large. So we would want to go with the left to right numbering or the blue numbering. So if we do that, we will then get, we have the methyls at carbon number 2 and 3. So again, 2, 3 dimethyl. Our ethyl group would be at carbon number 5. So again, E before M here. So the name here, putting all that together, let's go down here, I think. We will go with 5-ethyl dash 2, 3 dimethyl and heptane. Any questions on the naming of that there? Okay, let's get that. Let's also talk about, though, if you do have the name and you want to draw the actual formula for it, how you go about doing that. So if you're given the name and you want to draw the formula, truth be told, it is actually the easier of the two, I think, to do because pretty much they tell you everything. Whenever you have the name and you want to draw the formula, you always approach it. The best approach is starting at the back of the name and heading in that direction. And that's because the back of the name basically gives you how many carbons you should deal with. So when we see the name butane, butane is 4 carbons, which means what you want to start with is really just the carbons in this case. So leave yourself a little bit of room because you might have to fill some stuff in. So you just want to start with the 4 carbons, which takes care really of the butane part. We then have dimethyl. So we know methyl is a CH3. And di means that we do have 2 of them. And what that means is that is what the numbers here, right? So we have a methyl group at carbon number 2, and we have a methyl group at carbon number 3. The nice thing is, since you are drawing it, you could choose whichever way you want to go. So you could go left to right and call the guy on the left carbon number 1. You could also, if you wanted to, start on the right-hand side and go right to left and call that guy carbon number 1. I'm going to go left to right. So I'm going to call this guy right here carbon number 1. So that means that carbon number 1, then to the right would be carbon number 2. I would have a methyl group, so I would draw that in. Again, it doesn't matter if you drew it up or if you drew it down. It's all the same. And since this is carbon 1 on the left, this guy would be carbon 2. That means that carbon number 3, I would also have a methyl group that is there. And that takes care of this part of the name. So what is left to put in there is basically hydrogens. Yeah. So what you're going to put in at the end is hydrogens. Again, remembering the big key thing that carbon wants 4 bonds. Yeah. So when we look at the guy on the left, it has only 1 bond coming in, which means it needs 3 more bonds, and those 3 more bonds would come from hydrogen. So we put 3 hydrogens. The carbon right here at carbon number 2 has 1 line coming in there, 2 lines coming in there, 3 lines coming in here, which means it has 3 bonds, so it only needs 1 hydrogen. Same thing, the guy over here on the right, 1 coming in, 2 coming in, 3 coming in, just needs 1 bond and 1 hydrogen. The guy at the end has only 1 line coming in, he needs 3 hydrogens. This would be your condensed formula for this guy. So when you're given the name, again, sometimes very easy or a lot easier to do because you basically just need to draw what it says. So with that in mind, why don't you try the next 2 and then we'll talk about it again. Work from the back, from right-hand side to the left of the name. Okay, let us take a look. And to answer your question, we will not be having a quiz, obviously, since finals are next week. But this stuff will be a fair game for the final. So the final will cover everything. Okay, so when we're looking at this, again, we want to work backwards. So heptane means 7 carbons. So we'll draw it sort of like this: 1, 2, 3, 4, 5, 6, and 7. 1, 2, 3, 4, 5, 6, 7. So 7 takes care of heptane part. Now, ethyl means at carbon number 3, we have an ethyl group. Again, that's going to be a 2 carbon group, which will be our ethyl. And at carbon number 2, we have a methyl, which is our 1 carbon group. So just like before, since you're drawing it, you could go left to right and call the guy on the left carbon number 1, or you could go on the right and call it carbon number 1. You just can't change your mind. So whichever way you choose, you have to stick with it. So I'm going to go left to right. So the guy on the left here for me is going to be carbon number 1, which means that carbon number 2, I have a methyl group. So I'll draw my methyl group in. Takes care of that. Carbon number 3, which is right next door, is where our ethyl group would be. And that would take care of that. And now again, everything else is going to be hydrogens until carbon has 4 bonds. So guy at the end needs 3. Guy right here has 3 coming in, only needs 1 hydrogen. Same thing with the guy on the right. Guy on the next to those guys has 2 lines coming in, which means he needs 2 hydrogens to get the 4. Next one also needs 2 hydrogens. Next one needs 2 hydrogens. And lastly, guy at the end that has only 1 line coming in needs 3 hydrogens. Any questions on that one there? And looking at the last one here, again, working backwards. So pentane going to be 5 carbons. So that's what you want to start with, is 5 carbons. Takes care of the pentane part. Again, at carbon number 4, there's a methyl group, which is a CH3. And now carbon number 2, there's a chloral group. So we haven't seen chloral. Chloral is a halogen, and it is Cl, group number 7. So group number 7, those halogens, they do appear in a lot of organic molecules, and they're named kind of like this. So chlorine would become chloral. If you had a bromine, it would be a bromo. If you had a fluorine, it would be a fluoral. And if you had an iodine, it would be an iodo. So that's the only kind of weird one, like iodo or iodine. But chloral, bromo, if you had a bromine attached. So those are sort of how those guys are named. So it works kind of the same way. Again, I'm going to go left to right. And on my guy on the left is going to be carbon number 1. So right next door would be carbon number 2, which is where I would put the chlorine. That means that this guy right here is carbon number 3, and carbon number 4 would be here. And same deal, we're going to fill in our hydrogen. So he needs 3. This guy needs 1. This one needs 2. This one needs 1. And this guy at the end needs 3. So like I said, I think kind of going name to formula is actually the easier of the two, because they pretty much tell you where to draw everything, where everything is. Any questions on how to name or draw these sort of formulas? Yeah, so the idea with the hydrogens is when you're doing this, so the question is, how do you find out how many hydrogens? And it's based off of this idea up here that carbon pretty much needs 4 bonds. So if we just kind of back up where we just were, so let's go back this way here. Actually, what I'll do is get rid of all this guy here, and we'll just redraw this guy up here. So right before we finished that last guy, we were at this stage where we put everything on. So we had something that looked like this. So when we're trying to figure out at this point, after you pretty much put everybody on there, so we've got rid of this guy, we got rid of this guy, you know, we put everything on there. The only thing that's left at this point would be the hydrogens, and the goal is to get carbon to have 4 bonds. So the guy on the left at this point only has this bond coming in. I'll make it really big. It's a single bond still. But this guy coming in only has 1 bond, which means he needs really 3 more hydrogens to get him to 4. And that's why we put CH3. And that's because if I just draw that part out, really what he had was something that looks like this. So by putting those 3 hydrogens there, it would look something like this if you drew out that guy. And that gives this carbon here 1, 2, 3, and 4 bonds, which is what it needs. So we're kind of filling in all the rest of it with the number of hydrogens to get us to 4. We go to the guy next to him. We have 1 bond here. Again, this big bond here is 2. This guy coming in is 3 bonds to that carbon. That means he just needs one more hydrogen to bond in to get to 4. If we come to the guy next to him, it has one bond here, 2 bonds on this side. He's missing actually 2 more bonds. And again, that's going to be filled by 2 hydrogens. And again, if I drew that guy out, he would then look like this. Yeah. And that's why, again, we need those 2 hydrogens to get us to 4. And if we continue that pattern, 1 bond here, 2 bonds here, 3 bonds here. So he needs 1 more hydrogen. And the guy at the end only has 1 bond, so he needs those 3 hydrogens. He's just like the guy on the left-hand side. So that's, again, basically the goal here is to get carbon to those 4 bonds. And basically we fill it in with the hydrogens. Other questions on that? Okay. All right, so we're gonna kind of go through that. So let's just talk a little about cycloalkanes. So we talked, I think, about them a little bit before, but cycloalkanes are really alkanes where we kind of join the ends together, if you will. And by joining the ends together, they actually do lose those 2 hydrogens like we talked about last time. And cycloalkanes have the CnH2n formula. Again, they're missing that +2 part because they close in on each other and they have 2 less hydrogens. Here's a triangle, a square. A lot of times they are drawn in that line formula. And remember, in the line formula, everywhere there's sort of an end of a line or a point, if you will, is considered a carbon. So again, this is the same as this guy over here, the triangle. And cycloalkanes are named the same way. It basically has 3 carbons, which is based off of propane. And because it's a sort of ring structure, we put the cyclo in front of it. So this is cyclopropane, all one word. This is 4 carbons, which is butane, also in a ring structure. So we put the cyclo in front of it, and it becomes cyclobutane. There's cyclopentane, which is a 5 carbon ring. Cyclohexane, again, 1, 2, 3, 4, 5, and 6 carbons in a ring structure. And again, as we talked about in line structure, typically you don't put much in there other than the lines. But again, at each of these points, there is a carbon that's attached, or that's there, and along with the appropriate number of hydrogens. So how do we name this? We essentially will just put cyclo in front of it. If there is something attached, we basically kind of do it the same approach. So in this case, the big ring here, just kind of color it in, is the base of our name. So this is going to be cyclohexane. Again, it is 1, 2, 3, 4, 5, and 6 carbons together, which is where the hexane part comes in. The cyclo, because it's a ring. Just like the other thing, we do have some groups attached. We have a methyl group, and we do have a ethyl group here. Now, we do want to number this chain as well to give the locations, and we want to go with the smallest number. So if we start here, this is carbon 1, 2, and 3. That would give us groups at 1 and 3. We go the other way, you may be saying, if I go 1, 2, and 3, I end up with also 1 and 3. So that's sort of a tie no matter which way you go in terms of numbering between those groups, the carbons. But what's important, as we talked about in terms of the groups, is alphabetical order, which means technically speaking, E is going to come before M, which means we want to give that guy with the E the lower number, which means we would want to go this way here when we're numbering it, because that's going to give alphabetically the group with the alphabetical priority the lower number, and that would give us, if we put it all together the same sort of way, 1 ethyl, 3 methyl cyclohexane. So still alphabetical order. And in this case, when you do have a tie, you sort of want to go to the next important thing, which again is alphabetical in this case, and given that ethyl, the smaller number. Any questions on that? Now, if you just had something like this where there's just one group attached. The ring here would be cyclopropane because it's 3 carbons. Now, in this case, there's just one group attached, and because there's just one group attached, it's thought of always going to be carbon number 1 where that's attached, and you actually don't need the number. So this would just be methyl cyclopropane because there's only one group attached, so wherever that group is attached is going to be considered carbon number 1. When you have multiple groups attached, like we do here, you do have to give the number. So that's why we gave the number on the guy on the bottom, but the guy on the top does not necessarily need the number or doesn't really need the number because there's only one group attached. And again, wherever that group would be considered carbon number 1. This is what is sometimes referred to as being mono-substituted. It means one group attached, the guy on the bottom, di-substituted, which means there's 2 groups attached. And that's what we see here. Again, in each of these here, we just have one group attached. So that's a methyl group, and this is a 6-carbon ring, which would be cyclohexane. So that's methyl cyclohexane. Here is a long group of 4 carbons, and that's butyl group. And this would be cyclopentane. Again, no number here because there's just one group attached, so you don't need the number. Only need numbers, again, when there's multiple groups attached. All right. And that's what we did here. In this case, this particular one here, we would want to go 1, 3. And it doesn't really matter which way you go on this particular one because both groups attached are methyl groups. The only thing you would not want to do is like number this way: 1, 2, 3, 4, 5, 6. And again, this is why it says not 1, 5, because obviously that's a much larger number if you went that way. So we would want to go clockwise in this case, giving us 1 and 3. We still have dimethyl because there's 2 methyl groups in it. And again, we do have numbering because there's more than one group attached. That was the guy we just did, I think. All right. So let's just talk a little bit about properties to finish up here, just to make sure we sort of cover that part of it. Alkanes are nonpolar, and basically alkanes are all carbon-carbon bonds and carbon-hydrogen bonds. So those are nonpolar bonds, and they're going to use those dispersion forces as their main sort of source. And that means that they're not soluble in water because like dissolves like. So organic guys typically will not be soluble in water. So if you put an organic guy in with like water in a test tube, you will see different layers. And usually the organic layer is on top as it's less dense. The water layer, if you will, is on the bottom, and they will not basically mix with each other. And for example, oil is pretty much all organic. It's carbons, long chains of carbons attached to carbons and hydrogens. And if you ever seen an oil spill, it usually will just float on the water. And again, organic guys like alkanes being nonpolar. That also means because they're only using those dispersion forces, they typically have very low melting points and boiling points because they don't have a very strong intermolecular force, like we talked about with like hydrogen bonding or dipole interaction. So here you can see in terms of boiling point, they all use dispersion forces. The highest boiling point here in terms of all these alkanes is the guy with more carbons. And if you remember when we talked about intermolecular forces, the more molar mass there is, the more carbons there is, the stronger the dispersion forces that you will get. So in comparison of alkanes, the one that is larger in terms of molar mass would have more electrons and a higher boiling point, but they have a much lower boiling point than other organic groups as well. And in terms of reactions, typically organic guys will go through a combustion reaction. And a combustion reaction, the traditional organic combustion reaction looks something like this, but it basically is an organic guy plus some O2, and it makes CO2 plus water. And that is your typical combustion reaction. Remember, in a combustion reaction we talked about in that chapter, your typical products are always CO2 and water and oxygen involved. And with an organic guy, that's like when you light a Bunsen burner, the gas comes out. They're very flammable, right? And you'll get this combustion reaction. Obviously, it releases a lot of energy, like when you do a Bunsen burner, combustion engine, right? Those things give off a lot of energy as well. So here's another example of a combustion reaction. Again, methane, O2, we see CO and H2O. This is what is sometimes referred to as an incomplete combustion. So in a combustion reaction, we typically always get CO2 and water. If somebody ever says it's an incomplete combustion, the only difference is you get carbon monoxide instead of CO2. All right, so I think that is good. I think we're gonna call it a day. I got one more slide, I guess. We could look at this slide real quick, I guess. But basically, the other type of reaction that occurs with an alkane is what is known as a halogenation reaction, and it's what's known as a substitution reaction. And basically, what happens in a substitution reaction is, as we could kind of see in this picture here, one of the hydrogens come off. And this is Br2, which is basically two Brs. And one of these Brs goes in, or on, I guess. So in a substitution reaction with an alkane, which is really what happens, basically you take off a hydrogen. You can actually take off any hydrogen you want, and it gets replaced with one of the halogens. So if you had something like this, and you added it to Br2, which is this. Again, you could choose any hydrogen you want. You're just going to take it off. And one of these guys are going to come on in its place. And really nothing else changes, so you could draw it exactly the way it looked before. So if I just draw it really quick here, just exactly the way it looked. The only difference is the hydrogen that comes off gets replaced by the bromine that comes in. And if you think about what came off, you have a hydrogen that came off, and you have a bromine. And basically what those guys will come together will give you HBr. So that's the last sort of thing, just to kind of finish out this slide here. And I'll get your question here in just a second. The hydrogen and the bromine will come together to make HBr. All right, any questions on that? All right. So that does officially end Chem 2A in terms of lectures. Congratulations. Should be proud of yourself for hanging in there and continue to come and participate under these circumstances that we had. A couple of reminders, and again, I'll get to your question, which is what we're going to talk about here. Our final is on Monday, and it is, I want to say 8 o'clock is scheduled, and that's when you probably should take it again, so you don't run into any sort of conflicts with any other classes that you may be taking. So it will start at 8-ish. For you to take it. It will cover all the chapters that we talked about, so everything, including through what we talked about today. It's all sort of fair game. So there's a lot of material, but you just want to kind of think about other exams and stuff that we took and sort of the topics. When you think back on those, sort of the big topics, things like nomenclature, things like stoichiometry, conversions, obviously gas laws, those type of things. When you think back, it's kind of important topics. They probably will come back again. I'm not going to focus on any particular chapter in particular any more than any other chapter. So I honestly haven't written it yet. So it will probably, and they usually will end up being fairly, I don't want to say perfectly spread out, but it will be pretty comprehensive in terms of everything that we talked about this semester. It won't be like perfect, but it will be pretty evenly over all the topics. So again, I'm not going to focus more, say, on this chapter versus the other or anything like that. All right, first off, any questions on the final before I get to your question there? Again, I honestly don't know. Truthfully, I haven't written yours. I got one tomorrow. I'm going to start with that one first. That's the right. So I really haven't written yours yet. So I don't know. It may be similar to a regular exam, maybe have a few more questions, but truthfully, I haven't really written it or anything like that. Yeah, so again, you do want to start reviewing all that stuff from way back when. I don't remember when we started the semester anymore, but all that stuff that we did talk about. So you do want to review all those things. And again, you just want to think about, obviously there's a lot of material. So you want to think of, when you think back on things or you look at chapters, you think, oh, this chapter, this was sort of the main kind of big stuff that we talked about in terms of maybe calculations or stuff like that. So those are the things you want to kind of look at. Now, in terms of your question about the homework, I did sort of make a mistake in that sense. When I pulled it over for sampling, I forgot I did extend the due dates on those homework assignments. So obviously you still have the opportunity to do those homework assignments. And when you do those homework assignments, obviously in the end, it would be updated in terms of those grades. When I pull them over, because as I take it from sampling kind of by hand and move them over, I did sort of forget. I think I did extend those. So you still have the time to do those assignments if you have not completed them. And in the end, those points will be readjusted, obviously, accordingly. So um, that should answer that. Yeah. And what I might do is I'll take maybe those scores down off of the canvas for now. But that's sort of the deal. Yeah, I when I pulled them over, I was thinking in my head we already took the sort of exam on that, but I forgot I did extend them. So you still definitely have time for that. Also remember there might be another assignment or two up there that you do need to complete as well. So make sure that you do finish all of that online homework, obviously by the due date. And like I said, even if it reflects now a 0 and it's one of those assignments that hasn't been due yet, it will be changed for sure at the end. Now, in terms of grades and all that, I've gotten some emails and stuff on that. Just so we're all clear, we are still going with whatever it said on the syllabus in terms of grades and grade breakdown and anything that you're allowed to do. So again, whatever it says on the syllabus is what we're going to be following. And just off the top of my head, so again, refer to the syllabus for specifics because I teach 5 classes. But off the top of my head, I believe you'll get the opportunity to, I think, drop your lowest quiz, if I'm not mistaken. And I believe you'll also have the opportunity, if it does say so on the syllabus, which I think it does, that if your final is, again, a higher score than perhaps one of your exams, you'll get to replace that as well with your final score, your lowest exam. So again, I believe that's what it says on the syllabus. And if it does say that, that is, again, what we're still following. Obviously, whatever is posted right now has not been adjusted or anything like that. So, what you're looking at probably right now would be, I guess, your worst case scenario. Your real grade is probably a little bit higher than what you see right now. Again, after those adjustments are made, and they're not going to be made obviously until the very end because it's just a pain to do. So it can't adjust and readjust and stuff like that. So what you see now is sort of like your raw score up there and all that. And, it probably will be a little bit different, but whatever it says on the syllabus in terms of grade breakdown and what you get to do in terms of dropping or replacing, we will still do that. All right. Any other questions on anything like that? So again, congratulations on finishing here. You still have one more thing to do. Obviously, the final. Make sure you, again, take care of all that homework. I enjoyed having everybody in the class when I was able to see you in person and online as well. And I do thank you for continuing to show up and attending lecture and stuff like that. I wish you the best of luck on our final and all the rest of your finals and everything like that. And again, if you do have any questions between now, obviously, and Monday, you're welcome to email me and everything like that. All right. With that, I guess we will officially end the last lecture of the season here. Again, congratulations. Have a good rest of your day, a good summer, and all that good stuff. And, if you need anything, feel free to email me. Have a good one.